Welcome to our Bioprocess Engineering online tutorial on bioprocess design and scale-up. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. In this introductory tutorial on the design and scale-up of bioprocesses, we'll address three questions. What are the challenges of bioprocess scale-up? What are the bioreactor technologies in operation? What are the tasks of bioprocess design? Scaling up industrial bioprocesses is a major challenge for bioprocess engineers. Typically, bioprocess development initiates at the laboratory scale, utilizing small equipment, such as bioreactors ranging from liters to tens of liters in volume. Once the process is defined at this scale, the next step is scaling it up for production. Industrial bioreactors at this stage can vary in volume from cubic meters to thousands of cubic meters. The challenge for bioprocess engineers lies in swiftly extrapolating the process, while minimizing experimental work on pilot or industrial equipment. The initial phase in bioprocess scale-up involves outlining the process flow sheet, which delineates the sequence of unit operations, transforming raw materials into the desired product. Upstream operations typically encompass media preparation, thermal sterilization or filtration, and the biotransformation. Downstream operations, focused on product recovery, purification, and conditioning, vary in nature and quantity depending on the specific product. Minimal purification may be required for certain products, such as the production of a crude enzyme preparation. In contrast, more complex processes, like the production of highly purified therapeutic molecules, such as monoclonal antibodies, may entail up to 10 or more operations, including multiple final chromatography steps. After establishing the industrial scale sequence of unit operations, the engineer faces the crucial task of selecting the optimal equipment technology and operational mode. This decision often involves choosing between batch or continuous operational modes for certain unit operations. Another key aspect of bioprocess optimization is the consideration of operational variables within unit operations. These variables encompass temperatures, substrate and reactant concentrations, and flow rate. The ultimate goal of scaling up is to design an optimal process that maximizes productivity, minimizes production costs, and reduces environmental impacts to the lowest possible levels. The critical decision in bioprocess design and scale-up lies in selecting the technology and operation of the bioreactor, implementing the enzymatic or cellular transformation. Indeed, the biotransformation operation is particularly sensitive to the reactor configuration and operational conditions. Industrial bioreactors exhibit a wide range of technologies and operational modes. The design of bioreactors must be intricately tailored to the specific enzymatic or cellular biotransformation, accounting for the kinetic characteristics of the biocatalyst. Additionally, considerations must extend to the industrial context, including production scale, sterility requirements, and quality constraints. When scaling up a bioreactor for enzymatic or cellular biotransformation, the initial decision involves choosing between a soluble or dispersed biocatalyst and an immobilized or retained biocatalyst technology. Opting for soluble enzymes or dispersed cells presents the advantage of simplicity. On the other hand, immobilized or retained biocatalysts provide the opportunity for prolonged biocatalyst reuse, allowing operation under high densities and achieving enhanced productivities. The second decision involves determining the operation mode of the bioreactor. Reactors utilizing a soluble or immobilized biocatalyst can operate in three distinct modes. The batch mode, in which all the biotransformation substrates are introduced initially. The continuous mode, in which substrates are continuously fed, and products, along with biocatalysts, are continuously withdrawn. The semi-continuous or fed batch mode. This involves the initial introduction of part of the substrates, with the remaining portion fed continuously or intermittently during the biotransformation. Another crucial decision pertains to the bioreactor technology, especially when employing a continuous operation mode. The reactor can be configured as either well-stirred or tubular. An alternative approach involves employing a cascade of stirred reactors. For biocatalysts immobilized on particles or carriers, these particles can be employed in a stirred tank or in a tubular fixed-bed reactor. Moreover, the bioreactor can be integrated with a microfiltration or ultrafiltration module, functioning in a continuous perfusion mode. In this scenario, substrates are continuously supplied, products are continually removed, and the enzymes or cells are retained within the reactor. All these diverse bioreactor technologies and operation modes find application on an industrial scale. To illustrate the impact of the bioreactor technology, consider as an example the hydrolysis of starch maltodextrins into glucose using a glucoamylase enzyme. For a reactor designed to process 10,000 tons of maltodextrins annually, with an objective of achieving 90% hydrolysis, the sizing of continuous reactors under identical operational conditions yields significantly different required volumes. 70 cubic meters for the stirred reactor, 25 cubic meters for the total volume of the cascade of 4 stirred tank reactors, and 19 cubic meters for the tubular reactor. Consequently, the tubular reactor technology proves to be the most efficient for the continuous starch bioconversion. A second example highlights the impact of bioreactor operation mode in the production of animal cells. In this case, a stirred bioreactor is employed to propagate CHO cells, using a medium with glucose and glutamine as the primary substrates. When the reactor operates in batch mode, CHO cell growth reaches a maximum concentration of approximately 5 billion living cells per liter after 5 days of culture. Conversely, operating the bioreactor in a fed batch mode, characterized by intermittent additions of the culture medium, enables the control of glucose and glutamine concentrations at low levels throughout the culture period. Under these conditions, CHO cell growth persists, reaching a concentration of around 9 billion living cells per liter. Clearly, the fed batch mode proves to be the most suitable for the efficient production of CHO cells. In the third part of this presentation, we will delve into the sequential tasks performed by a process engineer throughout the design and scaling up phases of a bioprocess. The process design commences with the critical selection of the process diagram or flow sheet, outlining the sequence of operations essential for transforming raw materials into the desired final product. Once the flow sheet is established, the process engineer methodically conducts a material balance assessment, determining the sizes of unit operation equipment and evaluating their corresponding energy consumption. Subsequently, the engineer carefully scrutinizes investment and production costs, thoroughly assessing the environmental impacts associated with the proposed bioprocess. The final step involves bioprocess optimization, driven by considerations of both economic feasibility and environmental impact. The design task will be elucidated using the example of a fermentation process aimed at producing an enzyme. In the upstream section of the process, the unit operations include the preparation of the fermentation media, the media sterilization, and the actual enzyme fermentation process. Meanwhile, the downstream section involves centrifugation, ultrafiltration, and the final step of spray drying the enzyme. The biotransformation employs bacteria, capable of excreting up to 30 grams per liter of enzymes. It is carried out within a 10 cubic meters fermenter. The production process comprises a total of 180 consecutive batches per year. Materials consumption and production are initially assessed at each unit operation and across the entire process. For the enzyme production bioprocess, the annual consumption comprises 220 tons of glucose, 50 tons of salts and minerals, and 1,800 cubic meters of water. At the same time, the bioprocess yields 50 tons of powdered enzyme, 40 tons of CO2 from the fermentation process, 180 tons of solid waste resulting from centrifuge biomass, and 1,200 tons of liquid effluent originating from the ultrafiltration permeate. The sizing of the equipment is carried out on the basis of the quantities of processed materials and the time schedule of the operations. For the enzyme production process, the evaluated equipment sizes are 10 cubic meters for the media preparation tank, 50 square meters of surface area for the sterilization heat exchanger, 10 cubic meters for the fermenter, 10 cubic meters per hour for the centrifuge capacity, 15 square meters surface area of membrane for the ultrafilter, and 1,500 liters per hour for the sprayer dryer capacity. The operation of the process equipment necessitates two distinct forms of energy. First, electricity is consumed across all unit operations, particularly for tank agitation and fluid pumping. The electricity consumption for the entire enzyme production process amounts to 230,000 kilowatt hours annually. Second, heat is necessary for thermal operations, such as sterilization and drying. In the sterilization heat exchanger, heat is generated through a closed-loop steam circuit, which in turn requires natural gas. In the spray dryer, air is directly heated through the combustion of gas. These two operations contribute to an annual consumption of 75,000 cubic meters of gas. The initial phase of the economic analysis involves evaluating the investment cost, which encompasses the capital required for equipment acquisition, installation, and operational setup. In the case of the enzyme production process, this investment totals approximately €3,500,000. Subsequently, the second step revolves around determining the annual production cost per kilogram of enzyme. This calculation involves several components. The annual equipment utilization cost, comprising equipment depreciation and operational expenses. The annual material cost derived from the process material balance. The annual energy cost, directly derived from process energy consumption. And the cost of labor, estimated from the labor required to operate the production unit. The cumulative annual enzyme production cost reaches nearly €1,500,000, which corresponds to a production cost of €30 per kilogram of enzyme. The environmental impacts generated by a bioprocess are thoroughly assessed utilizing the life cycle assessment, or LCA methodology. In the evaluation of environmental impacts, key indicators are derived from the process material balance and energy consumption. Specifically in the context of the enzyme production process, the three key impact indicators are as follows. 200 megajoules per kilogram of enzyme for primary energy consumption, 110 kilograms of water per kilogram of enzyme for water consumption, and 11 kilograms of CO2 per kilogram of enzyme for the global warming potential impact. The ultimate objective in bioprocess design is to optimize the operating modes and variables of the unit operations within the chosen process scheme. This optimization can extend to considering process integration schemes, including water or heat recycling between unit operations. Typically, process optimization is oriented towards economic efficiency, with the primary goal of achieving the lowest production cost per kilogram of the desired product. Additionally, this optimization may encompass environmental considerations, striving to minimize the impact indicators generated by the process. This dual optimization approach ensures that the bioprocess is not only cost-effective, but also environmentally sustainable. In conclusion, in this introduction to the design and scale-up of bioprocesses, you learned the challenges of scaling up bioprocess from laboratory to the production stage, the need to customize bioreactor technology and operations based on the specific biotransformation in the characteristics of the employed enzymes or cellular biocatalysts, the tasks of bioprocess design encompassing the determination of material balances, sizing equipment, assessing energy consumption, conducting economic and environmental evaluations, and optimizing the overall process. If interested, you can gain a deeper insight in bioprocess design and scale-up by enrolling to one of our 2 online courses, Introduction to Bioprocess Design, Scale-Up and Simulation, and Design and Cost Evaluation of Bioprocesses. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.